Hello, my structural analysis friends. In previous videos, we've been talking about influence lines and how we can use those to work for beams and frames and all sorts of other systems. Well, in this video, I'm going to show you how to do it for trusses. So without further ado, let's get started. So in this lesson, we're going to kind of work our way through an example and kind of illustrate the process. To this point, we've dealt with beams and frames, and the concepts that we dealt with there are very, very similar with what goes on in trusses, although there is one little difference that we'll have to work with. So for us, to kind of set up this particular lesson, let's take a look at a simply supported truss. It's an equilateral truss. It has 20-foot spans here, and 60-degree equilateral triangles make up the body, which gives us then a height of something like 10 square root of 3. If you remember your 30-60 triangle, it's the 1, 2 square root of 3 triangle is where that square root of 3 is coming from. And we'll see that square root of 3 kind of run through this example throughout. The process is very similar. The way that truss diagrams work for influence for trusses is that we know that truss members are subjected only to axial forces. So if I want, say, the force in FGB, then I would have to cut it and go through all my truss analysis methods, method of sections, method of joints, what have you, to find that force. The only difference now is that I have a traveling surface. Say it's the road for a car or a bus or something, and it's moving on here, and then it loads onto the bridge and moves all the way across and then comes off eventually. So this is what we call a kind of a normal wearable surface on this particular truss. Now, you can't have trusses that are underslung, in which you would be driving across the top, so you have to know where your travel surface is as you start to set these up. For us, for this example, we're going to assume that the travel surface is on the bottom here. Now, all we do is we kind of set up our approach the exact same way, is that I'm going to move this force from point to, along this travel surface as some variable of x, usually listed as the reference at A, as my reference here, and then we're going to compute the effects of putting that load at different locations, right? And so when we did it for beams, we did something that kind of looked like this, okay? That for a load that's given at any x, we know that a reaction AY was 1 minus x over L, where L is the span, and then dy was x over L, okay? Trusses have a little bit of a bigger complication to them, okay? Our diagram would look something like this, conceptually. Okay, where my one kip load is now at a distance of x, I set my reference at the corner of A. Okay, and this is the picture that you would get for x being anywhere between 0 less than or equal to x less than 60. The problem has to do with the loading on this. In a truss, remember that we are bound by the rule that loads have to be applied at the joints. Okay, and so there's a whole lot of x values in the middle of this that are not at the joint, so we have to make a little bit of a shift. Okay, and so let's see. If we look at the basic picture, one might start to look at setting it up as so. Okay, suppose we want to find, say, FGF, which would be my member across the top here, and in this truss it'll be a compression member, okay, for any function of x along the travel surface. Okay, so your classic methods say that to find FGF you would draw a free body diagram that looks something like this. And so here's my one kip sitting here at an x. This was my reaction from the original picture, and then I have my 3 unknown forces here. Okay, FGF being the one that we're after, this guy up at the top. Now this is the picture that's valid for 0 less than or equal to x less than 20. Okay, but as we said, this load has to be applied at the joints. So I can't solve this one because this isn't a truss technically, because if I were to apply this load to this member, this guy goes into bending. He's no longer axial only. He's a flexural member. Okay, so for it to be a truss, I have to somehow get this load passed out to the joints on either side. And so this is what we're going to look at. Okay, and we're doing it. Okay, so if I have an arrangement that looks something like this, here's a member that's located at x from 1 and has a load somewhere along his own member. So if I put a joint there and a joint there, that I can pass this load out as such that the amount of this load that travels to this direction would be 1 minus x over 20. Okay, and so this load would put that amount of load at this point, and then at the same time, at the other end, it would be an amount of x over 20. Okay, and so let's test this out. So if my load were sitting over here at the far left end, x is 0, the full amount of 1.0 goes into that load right there. That's exactly the picture that we have. And likewise, if x is equal to 0, this would be 0. And so because none of the load would travel into this joint, it would all go through here. All right, so that seems pretty logical. And if we test it the other way, if I go to x equals 20, then this guy becomes 0, and this guy becomes 1. And so this is the way that I can distribute these loads to the node. So it's over the member that it's acting, okay? If you notice this may look familiar to you. 1 minus x over L, well, that was our reaction for simply supported reaction at, say, the end of A, at the beam. That was this guy, okay? And likewise, the other one, which is x over 20 or x over L, would be the other one. So this is basically a beam analogy hidden inside of the truss, but now we have to work with basically a system of 2 loads. And we'll use this idea of multiple loads as we move into girders and other structures as well. All right, now that's all fine and dandy for us when my reference is located at the left end of the node. We knew it was 1 minus x over L and x over L. But the problem that we have is that as our loads start to move along here, in the first span, we're looking at this span, which it works, but then in the next case, the load's going to be over in this area, which means now my reference is no longer at x equals 0. It'll be at x equals 20 or some other point. So we've got to come up with a way to shift our coordinate systems. And I'm going to show you a little derivation and a trick for the way that I remember how to do this. Okay. All right, so here we go. So it's the same basic idea. So here's our beam, and we're going to put a 1 kip load on this beam. The beam has some length of L, okay, there, and we're going to call the distance from the reference here to where the load is acting on the member as some value x prime. Okay, because remember, when we make influence lines, we choose a reference for the whole system, and then x is always measured back to it. So, even though technically I'm at x prime from the left end of the member, I'm x from my reference location. Okay, so to make this work, this shift occurs in this, what we call this offset amount that we're going to call as delta x. Okay, so if we look at this, the original derivation that we have for this 1 kip load would be that the reaction load here would be 1 minus, and that should be an x prime amount over 20, and then x prime over 20 for the other side. That's what we had here. But the problem is that nowhere in this is my original variable x. All right. Now, if we look at the relationship between these 3 guys, we know that x is equal to delta x plus x prime. Okay, which means that I can rearrange and solve for x prime as being x minus delta x. Okay, which that's the variable that I want. And this x prime distance is basically a function of the offset amount. So if we look at the picture that we just drew, here's my x prime. All I'm going to do is I'm going to substitute in x minus delta x for that. And so now for the load based off of our reference over here at 0, the load on a member, is now listed as 1 minus x minus delta x over, I'm using 20. This is the length of the member. It should be this guy here. So I call it 20 for this example. It could be something different, but it's that guy. And that's my L that I'm talking about. Okay, and then the other end is x minus delta x, or x minus 20 all over and that is, wow, over L here. Okay, and I'm going to go ahead, and since I'm erasing stuff anyway, I'm going to make this an L here also. All right, and so that's the way that we would, for the L being the length of the member that the load is sitting on. Okay, and this should be, and this kind of idea of being able to pass the loads out to the joints should work, is pretty legitimate. Okay, I don't want to, that sounds bad when I say that, but we know that for a truss, that if I have members going across, the framing on most bridge trusses, I generally have 2. Let's see, let's draw something, whip something in here real quick. Truss like this, and then over on the other side, on the near side, we would have another one that looks something kind of like this. The 2 parallel sides, and 1, 2, 3, 4, 5 would look something, again, very crude, but hopefully illustrates the idea that we're trying to get across. Did I lose one? I lost one. Something kind of like this. But what happens is that, oops, I guess I should have one in here, here. Let's do this right. That's what I get for freelancing. Let's, okay. And we're going to fix our section here a little bit. Get this drawn in there. Instead of getting in a hurry, we'll do it right. This and this. So let's do this one, this one, this one. I just want to make sure everything lines up at the panel points. This, 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 and this. All right, so we get something like that, and then something like that, and something like that. And then this one, I end up with one here. I end up with one there, so that's this guy, that's this one, and then one. 1, 2, 3, 4. 1, 2, 3, 4. There we go. Looks something like that. There we go. Got my pictures straightened out. So that would be my truss like this. And so what happens is the truss is what is used to span the river or the valley or the gorge or whatever. And then there's these girders that transfer across on here. Now the road deck is a result of a vehicle moving down this way. Well, in between these girders will be a series of secondary beams, okay, down the length of the path that basically transfer the load from the slab and any vehicle out in the middle out to the girders. So that's how we were able to ensure that I get point loads on this particular truss. All right, sorry for the long-winded explanation, but this is a valid kind of idea. And so you can kind of see that's what's happening with these pictures here, that we're basically taking that one kip load that was out here in the middle, and I'm transferring it out to the girders, if you will, and then this is what's sending the loads into the truss themselves. Okay, all right, so that's kind of what we're looking at. All right, so let's get back to it. All right, so if I play the game, we're looking for the behavior of the force FFG here, okay, and so you can use your truss analysis. And if I want this guy, we know that I could cut through the members FFG, FBF, and FBC, and then I could apply my loads as is the case here. So for this one, we had 0 less than or equal to x less than 20. Okay, my delta x offset on this is 0. All right, because my reference is here, but it's also the reference of the member that has the load. Okay, so if I do that, then the reaction load, I have the reaction here, which is AY. Okay, and then I get the portion of the one kip load that shows up at the left end, 1 minus x over 20, and then a portion of it that shows up at the right end, which is x over 20. Okay, and then I have my 3 unknown forces, and likewise I could work off of either side, whichever one is more convenient. They both get you the same equation. But if I go through and I do my truss analysis, and again, if you're struggling with truss analysis, go back and watch our videos on those in the static section. It's not a problem. Okay, but I can go through and I can sum moments then at B and solve for the force FFG. And so we can see that for the first span in this interval, FFG is going to be minus 2 times x over 30 square root of 3. Okay, which basically means that when x is 0, FGF is 0, and that should make sense, right? We're looking for a force here, but if my load is sitting at this point, all the load goes into the support, nothing shows up in this member. So that jives. Okay, and then the other case is if all the load is sitting here at 20, FGF, if I plug into this equation, then has a value of minus 0.77. Okay, and we can repeat this process for all the other sections. So I'll draw you the pictures real quick. We won't do the statics, but I'll at least kind of show you the formulas that go in here. So here's my original one. Now one kip is now in between 20 and 40. So this was 20, this was 40. Okay, so I got to take this load and pass it to either side, and so that's what we do. And so at B, I end up with a 1 minus. Now in this case, delta x is 20 because the left end is here, but my reference is still here. Okay, and that was 20 feet from this location to here. So that's how I know that this is 20 feet. And so then it's a reaction of 1 minus x over 60 here. I get the load from the one kip that is 1 minus x minus 20 over 20 because we're taking it over the length of this guy. And then x minus 20 over 20 is the reaction of this guy for the other point load. So basically I'm taking this one kip load and I'm splitting it into 2, 1 at each end of the member. Okay, and then I also need the reaction out here at D for the amount of x over 60. So if I go through and I draw my free body diagrams again, now we have, you know, a picture that looks something kind of like this. I'm going to use the same cuts on this, and so now on the left piece I get one of the loads because that's sitting here at B. That's the first load, 1 minus x minus 20 over 20, and then on the right piece I get the other one. Okay, so only one of them shows up on the free body diagram, and that's because we're jumping across. And so you can do your statics, you can solve for that, and if I do the statics for it, you find out that FFG is a minus 1 minus x over 60 times 2 over the square root of 3. Okay, and if we plug in our values, at x equals 20, it's a minus 0.77, and at x equals 40, that equation gets me minus 0.385. Okay, but you can see how the pictures are changing. It's the same process, it's just now the pictures, the loads are being differently applied because this is the span where the 1 kip load is sitting. It's in between. It just happens to be the one that we're cutting. Okay, all right, and then we go on and we can do the same thing for the last span, and that should be 40 less than x less than 60. Okay, now my delta x is 40. Notice that the delta x is the lower bound limit on this inequality. Okay, and so when I do that, now there's nothing on this guy. Okay, my cut is still coming through the middle. And then my distance now, I have a point load, and again, the 1 kip load is sitting out here in the middle of that last span. So at the left end, it is x minus delta x is 40, so x minus 40 over 20 gets me that one. And then I have an x over 60 is the reaction dy, but I also get that second load here, x minus 40 over 20 for the reaction here. All right, and that should be a 1 minus that value. Okay, all right, and so we go through, and if you do your algebra, this is the equation for FFG. And we'll take that off of there. Okay, and so now we plug in our values. At x equals 40, FFG is minus 0.385, and then at x equals 60, its FFG is equal to 0. Okay, and that's what you would expect. Again, point load sitting over on top of the support, that load's not going to travel through the truss to go through the member, so that's what you would expect. Okay, once you have that, then you can go in and you can actually draw the influence diagram for this particular member. So the influence factors for FFG then, if I plot the function of x equals 0, 20, 40, 60, these are my points, and I can plot my points, I get a shape that looks something kind of like this. This is the influence for member FFG. So now you can say, well, where do I put this to get me the worst load in that member on the truss? And you would say, well, clearly it's located at 20 feet. And we can go through and we can kind of look at that. But we notice that in all cases, this guy is always negative. So for a load that's acting downward positive, okay, this guy will always be a compression member. Okay, and that's kind of interesting. Okay, now, just like what we did before, once you have the diagram, say that you know the value of the load. Say it's 10 kips, and I want the maximum value. I would put the 10 kips here, I multiply it by its factor, and I would know the maximum load in FFG for a 10 kip point load anywhere is 7.7 kips. Okay, and we can start to use this for multiple loads like we talked about in the last video and kind of start to extend the exact same game. Once I get this diagram, everything else is the same that we did for beams. Okay, but it's just getting to this diagram has a couple little tricks to get you along the way. Now, I'm going to show you one other one because truss diagrams can do some funny things sometimes. Let's go back to, let's see if I can find the page here for our original picture. Okay, that say we want to find FFC, and this is C here. I want to know what's going on with this member across the web. These web members do some funny things sometimes as we start to move loads. Now, we have a simply supported truss. The same process works for cantilever trusses or whatnot. You just have to reset your equations for the supports. But we're after what's going on with this web, and that's the FFC member. So I didn't draw all the free body diagrams, but I just kind of ran the equations out for you. And so my FFC equation here is minus x over 30 square root of 3. If I plug in x equals 0, x equals 20, I get a 0 at the first point, what we expect, and my FFC is now minus 0.385. So it's a different value than what you saw. Okay, and if I repeat the process, what you can see is that in that middle span from 20 to 40, here's my equation, pretty complex. When x is 20, it's a minus 0.385, but when x is 40, it actually flips signs. And so this guy goes from tension to compression depending on where the load is at on this particular member, which is kind of an interesting phenomenon. All right, and then the last one from 40 to 60, playing the exact same game. Here's the equation. X equals 40, x equals 60, I'm at plus 0.385, and then at x equals 60, I'm back to 0. All right, and so if I plot it, then the diagram for influence for FCF, in this case, looks something like this. You basically plot the points. And you can see that this guy goes from tension to compression depending on where the load is on this. So if I want the maximum compressive load, which would cause the member to buckle, I put the load here at x equals 20. If I want the maximum tensile load, I put it at x equals 40. Okay, and so then you would have your design parameters and be able to know everything about that particular member, and that's the power of what the influence lines are. There's no longer any doubt, well, where do I put this to get the maximum value? Now, unfortunately, trusses, they're kind of long. You have to resolve the trusses, for however many panels you have, and for big trusses, this becomes very complex. But in general, it's a very straightforward process to be able to calculate influence lines for trusses once you get the load spread out. Everything else is the same as beams. It's just that we have to be able to get that one kip load spread to the ends with that offset. And that's the trick for influence lines for trusses. So I hope this has made some sense to you. If you got any questions, please leave some comments down below. As always, let us know if there's anything that we can do to make the experience a little bit better, a little bit more clear. And if the video helped you out at all, please like or subscribe to us, and we will see you next time. Happy engineering.